Hello, and welcome to this presentation on building energy efficiency as we look at the requirements found in the 2020 Bangladesh National Building Code. I'm glad that you could be here today. A little bit about me. My name is Shauna Mozingo, and I am the president of the Mozingo Code Group. I've been a plans examiner and a building inspector for around 20 years, and now have my own consulting company where I still do plans examining and building inspection, but I also help jurisdictions around the U.S. and internationally move to newer building and energy codes, and I also provide education on those codes that they've adopted. I take part in the code development process at the national level, participating in the International Code Council's code development committees and attending code hearings. I love to consult and teach on all of the family of I-codes, but probably best known for my work in energy codes. I was awarded the Department of Energy's Jeffrey A. Johnson Award, ICC's and IMT's Standard Bearers Award, and the Southwest Energy Efficiency Project's Leadership in Energy Codes Award for some of my work in the advancement of building energy codes and performance. I serve as an inspector for the China and U.S. solar decathlon competitions, many of them, and I co-authored the book, The 2018 Energy Code Essentials for ICC. I am also past president of the Colorado chapter of ICC and co-chair of the Education Committee. So education is a top priority for me. I love to teach, and I'm excited to be here to present the energy efficiency requirements as found in the Bangladesh Building Code. So let's get started. The Bangladesh NBC places a great deal of focus on energy efficiency of buildings throughout the entire document. We're going to touch on all of it, but we're also going to start, right here in the heart of the requirements by going to Volume 1, Part 3, Chapter 4. That's where it gives the overall energy efficiency requirements for buildings before sending us to some other sections of the code for other requirements. So here we go, Volume 1, Part 3, Chapter 4. That's where you're going to find energy efficiency and sustainability. So diving right into this first section of Chapter 4, the rationale for sustainable green buildings. The rationale is, it gives actually the best introduction into energy efficiency code requirements and into this entire session, really. So it reads that, first of all, climate change is an established phenomenon affecting the environment globally, and it's recognized that the building and the built environment play a vital role in the process, impacting on natural environment and the quality of life. Sustainable development concepts and approaches applied to the design, construction, and operation of the buildings or to any built environment can enhance both the economic and environmental benefits of the community in Bangladesh as well as around the world. Energy efficiency and sustainability is not an individual issue, rather an integrated and inseparable part of the building design and construction process. The benefits of sustainable design principles include resource and energy efficiency, healthy buildings and materials, ecologically and socially sensitive land use, and strengthen local economics and the communities. Objectives vital for future development of Bangladesh. I agree. So this is a great rationale. When we look into Chapter 4, the rationale sets us up to tell us, here's why we're doing this. Here's why we're getting ready to tell you what you need to do. And so then we go straight into Chapter 4. The section on site sustainability deals with sites to ensure the energy efficiency through passive and low energy architectural features and management of resources. We're going to look into each of these subsections to identify the requirements and discuss how they're meant to work. But first, I just want to point out that a lot of people look at this and say, okay, we were going to do a training on energy efficiency of buildings. And so that is true. But in Bangladesh's code, they've really put a stress on the cohesiveness of the entire project. And so how does it all work together? And so within the energy efficiency of buildings section, there is also, it deals with things outside of the building. Sustainable site. How do we deal with these unpaved areas, right? Site or deal with site drainage or vegetation or irrigation, rainwater harvesting. We're going to touch on all of those because anything on the site is included in this energy efficiency chapter. So let's look. All right, so the first subsection that we come to is 4.3.1, mandatory unpaved areas. So what this is telling us is that 50% of that mandatory open space has to be permeable on sites of all occupancy categories. So this applies to all occupancy categories, doesn't matter what type of building is going to go on that site. The permeable area shall not remain bare, generating dust, but will have green cover or be treated with perforated paving, at least 50%, organic mulch, charcoal, etc. So what is etc.? Maybe there's some pervious paving, some concrete, like is shown here on the right. When you look at this, is a pervious concrete. So just wanting to look at this site and make sure that we're creating a site that isn't going to have a lot of dust, isn't going to shed water, but is going to actually absorb the water. And how are we going to do that? So it's asking for a permeable site. What is permeable? So if you look at the definition of permeable, it says, a material or membrane allowing liquids or gases to pass through it. Okay, so that could be the vegetation. It could be some type of surface that we use. It also says if you're not going to do green cover, maybe you do a perforated paving. So what is perforated paving? Perforate just means, to poke a hole in it or something. And so maybe you have a pavement that has holes or perforations so that the water will go through and not run off. Trying to deal with a lot of that runoff and handle that. So one thing that I want to talk about too on a lot of these requirements as we go through them is how do we actually verify them? Who verifies them? So if we're looking at the site, a lot of times that's maybe not the building official. Maybe that is, in this case, when you're dealing with this mandatory unpaved area and this site. Maybe that's the Public Works Department, maybe that's the Engineering Department, maybe there's some planning involved. It's hard to know, but what are they looking at? They're looking at the percentage that at least 50% of that site is permeable, and they're looking at the different ways that it's permeable. Is it the vegetation? And if it's a paving, is it perforated? Is it some type of pervious surface that's allowing the moisture to go through? At plans, it does have to be submitted on the plan, so the plan reviewer is looking at it, but usually, again, that's not, the plan reviewer for the building is not usually looking at site stuff. So you just have to make sure that this is figured out ahead of time of whose job it is to look at these different things, and that they actually know that it's in the code, right? So a lot of times we put things in the code and then we assume that the people that have to look at them know that they're there. Well, not everybody looks at energy efficiency requirements. And so we need to make sure that if this is a planning or this is a engineering or this is public works or whoever's looking at it, that they are also mindful that there are these energy efficiency requirements in the building code that might apply to them. So just making sure that we communicate. Then we talk about section 4.3.2, site drainage and runoff coefficient. This is just a section that lets us know that the design has to indicate site drainage considerations along with flash flooding and erosion prevention measures. It only applies to sites above 1,340 meters square in area, but when you think about it, you have all of this paving. If it's not pervious or permeable, then it adds to the problem of the flooding that happens. And so huge paving area where the water runs off and you have flash flooding, that adds to the problem. So what we're trying to do here is have a design that indicates measures taken to make paving permeable. Let the water go through instead of over and across. So it says the net runoff from a site shall be a maximum of 60%. 60% of the site of these paved areas or of the site have to be pervious. So how do we calculate that? Well, it goes into a calculation. It gives us a method for doing that. So it says the following method will be used for the calculation. So it gives us a table here, and it tells us in a calculation that the site perviousness, AP, is A1 times C1, which means A1, the type of material, what is the surface that we have on our site, and what is the runoff coefficient for that. So we're looking at, we might have a paved site with brick paving or gravel or concrete paving. What kind of material do we have? And we'll multiply it by this coefficient here to figure out how much of our site has to be pervious. Maybe not the whole site, but a good portion of it or a portion of it depending on what we have. So let's give an example. Let's say that we're going to use concrete, right? And so we have concrete, maybe we have 1,500 meters square of concrete on our site. And so if we look at that, we have to do the calculation and we find in the table concrete. So we have some concrete paving. Concrete paving says we have a runoff coefficient of 0.95. So we have 1,500 square feet of concrete times 0.95 equals the amount of perviousness we need. So we can see that we need 1,425 meters square perviousness out of that concrete. So not all of the concrete has to be pervious, but we need 1,425 meters square of that. Now, you might have different surfaces on the site. Maybe part of it has vegetation. So how much vegetation? Here's your coefficient, and you would do the same. What is the square, or what is the meter square, the area, and what is your coefficient? And you'd come up with that. So you would do this calculation for each different surface so that you could eventually, you are looking at the entire site and how you're dealing with your water runoff, or hopefully lack thereof, and absorption. Okay, so the next section, 4.3.3, Vegetation Plan. This lets us know that for sites that are above those 3 acres, it's mandatory for a vegetation plan to be submitted along with the site plan and the irrigation plan, and that priority is given to native plants in the selection of planting. So when you're determining what plants you need to plant on the site, you need to start with the native plants for that area. And different areas have different native plants. So how do we verify this? This usually comes into like the planning department, maybe some civil engineering that has a list of native plants for the different areas, usually has requirements on the number of trees you have to plant or the number of the different kinds of bushes and the sizes that you have to plant and where they have to be located. So this is generally either like a planning or a civil department type of verification on that. And then it's also asking on 4.3.4 for an irrigation plan, but it's only for sites above 10 acres. It says an irrigation plan with the construction details shall be submitted with the site plan, where considerations shall include the management of rainwater. So we're going to have this site plan, and it also says that for the site plans there is a retention pond requirement. So the site has to have a retention pond of at least 3% of the site area to be provided. This includes any existing natural bodies on the site. So if you have an existing pond or lake or some other way of retaining the water, that's included in that. So this is really just wanting to, let's look at the whole building site. We look to see that we have some vegetation on there, but now how are we irrigating? How much of it are we irrigating? What are we doing to retain any water that might flow from rain or from other of those surfaces, right? That are not being absorbed. Where's that water going? How are we going to do that? How are we going to deal with that on this site and make sure you turn that in? Section 4.3.5 deals with rainwater harvesting systems. So this lets us know that when we have a building that is more than 4,000 meters square, it is going to have its own rainwater harvesting system. So it does tell us the rainwater harvesting system is going to be done in accordance with Chapter 7, Part 8. But it tells us here, if you're over 4,000 meters square, you have to have this rainwater harvesting system. And the only other thing it gets into is how to size the capacity of that reservoir. And a couple minor things. The rest of it sends us over to Chapter 7, Part 8 to see how it needs to be installed. We're not going to jump over there right now because I want to try to stay in this energy chapter as much as possible, but we definitely are going to talk about Chapter 7, Part 8 here in a little bit. So the other thing that this is telling us is that we need to size that reservoir capacity so that it's sized correctly, and it's based on it says the reservoir capacity has a size requirement where the code states that it shall be a multiple of the area of the ground coverage of the building and a rain collection coefficient, so of 0.073. So what is the ground coverage of the building? So let's come up with an example of, let's say that is 100 meters squared, just for ease of calculation. So we have 100 meters square of ground coverage of the building times the rain collection coefficient of 0.073. That tells us you come up with 7.3. So I need a reservoir capacity of 7.3 meters. Now it tells me that the rainwater reservoir may be placed under the roof or at a lower level, including underground. So it's not real specific on how you do it. There are some different methods of doing it that are discussed over in Chapter 7, Part 8, but this is just saying you don't have to choose one. It's saying, however, that it does apply to buildings over 4,000 meters. So need to keep that in mind when we jump over to Chapter 7. That gives us a different metric of when it applies. So we'll pay attention to that. When it comes to verification of this measure, what is it that we're looking at and who looks at it? Well, it could be a combination of maybe public works or utilities, whoever handles your water connections and those types of things. And it could be the building inspector and plan reviewer. So it depends on where really that reservoir capacity is going to be installed. So if it's going to be installed on or in the building, definitely we're going to look at it at plan review to make sure that the structural calcs have taken into consideration the amount of weight that's going to be involved in that. If it's going to be outside or underground or on the ground, then it's more typically not the building department. It's more typically your public works or somebody like that. And so just wanting to verify structurally the building can handle it, has it been sized? The reservoir capacity been sized correctly? What kind of materials are we using for the piping and for all of the connections? Making sure that we have those done. So that could be a combination of plumbing inspectors or public work inspectors to look at all of that. So that's how you would look at rainwater harvesting. All right, so we've talked about the building site and what we have to do outside of the building. Now we're going to focus on the building itself. How does the building itself perform? And so what are those things that do make the building perform? The things that this code has focused on are windows, shading, and the roof. And so those are the part of the building envelope that we're really going to look at right now. First, for windows. So in section 4.4.1, it tells us that for mechanically ventilated and cooled buildings, all occupancies except hazardous and storage, right, the window to wall ratio of the building will be determined in conjunction with the glazing performance, the solar heat gain coefficient, and the shading coefficient of the glass we use. So there's a link, this relationship between how much glass we use and what kind of glass we use. Right? So this is shown here in this table in figure 3.4.1 that's in the code that shows us that how much window to wall ratio do we have? How many windows do we have in our wall? What's the area of that? And here's our solar heat gain coefficient. So if you look at this table, we have different solar heat gain coefficients that we'll get to in a bit. Solar heat gain coefficient is looked at as a lower the number, the better. So if I have a 0.1 solar heat gain coefficient, that's letting me know that only 1/10 of the solar heat that's hitting the window is actually making it into the building. But if I have a 1, that's saying 100% of the heat that's hitting the window is making it in the building. Boy, I better have a good air conditioner to make up for all that heat that I'm letting into the building, right? So you can see that the lower the number, the better. What this chart is showing us, and these tables are showing us, is this relationship between the amount of windows and the type of windows. So you can see if I have a bad window, I can have less of them. But if I have the better window that I have, the more the code will allow me to have. So window to wall ratio, same in this, is this just tabular form of saying the same thing, that depending on how much windows I have, lets me know what kind of window I can have. If I have 90% of my area is in windows, I have to have a really good window. If I only have 10% of my area in windows, I can have a worse window. That's what that's trying to let us know. The code also has this, tells us that the visible light transmittance, VLT, it's referred to, of the glazed element shall not be lower than 35%. So what is that talking about, VLT, visible light transmittance? This is really a requirement for a manufacturer to make a good window. So what happens is a lot of times when we have to get those low solar heat gain coefficient windows so that it doesn't allow a lot of heat into the building, sometimes in order to do that, the manufacturer of the window will put extra films on it or do different things, and it makes the windows darker. Well, we run into this problem where if we have this dark window, what happens? We have to turn the lights on in the building. So are we saving energy? No, we're just changing the energy use from maybe saving some on our mechanical equipment, but now we've turned on lights. So this requirement for VLT is saying that you still, manufacturer, have to make a good window that doesn't allow so much solar heat gain, but at the same time, it can't be so dark that we have to turn the lights on. So it's just asking us to pay attention to that, and can't be lower than 35%. The VLT shall not be lower than 35%. That's what that's talking about right there. All right, what is solar heat gain? It seems like a big word. Solar heat gain coefficient. It seems so technical. And if you want the technical, yes, there is one. The solar heat gain is the fraction of incident solar radiation emitted through a window, both directly transmitted and absorbed, and subsequently released inward. It's expressed in a number between 0 and 1. The lower the window's solar heat gain coefficient, the less solar heat it transmits. So, what did I just say? That is really the layman's way of putting this is to say out of 100% of the solar heat that's hitting this window, how much is coming in, how much is being radiated away. So if I have, for instance, a solar heat gain coefficient of 0.40, this window is a SHGC of 0.40. That means that out of 100% of solar heat that's hitting the window, 40% of it is making it into the building, 60% is being radiated away. Why do we need to know that? Well, if I am in a hot climate that uses my air conditioner all the time, I want to pay attention to the kind of window that I'm using, because that window is going to either allow a lot of heat in or not very much. And so the requirement would likely be that if you're in these really hot climates that use air conditioning, you would want to put in a better window to not allow that heat to get in there, because you have to think about this too, that it's not, you have all the heat that's coming in through the window, and then you have all this ventilation air that's required for buildings so that people can breathe and that the building can breathe. That all of that ventilation that's bringing in air at whatever temperature it is outside, usually, unless you're using an energy recovery ventilator. So you bring all of that air in, so that's adding to the load that the either the furnace or the air conditioner has to offset. Then you take on that the people that are in there, people like me that, I have full of hot air. No, so we have all these people in the building. Then we have equipment, computers and monitors and copy machines and things like that that put off heat, our data equipment, our servers that are putting off heat in a building. All of these things that are adding to this internal load that are saying, all right, air conditioner, you're going to have to kick on, and you're going to have to really make up for all of this extra stuff in this building to cool it, to keep it at the right temperature. So we look at all of those things, and hopefully maybe we can't control the number of people that are in the building, or the amount of equipment that we need to use every day, but we can maybe control the kind of windows that we put in, or deal with the type of ventilation that we bring in, or deal with the lighting. There are things that we can deal with, and so that's what this is looking at for solar heating. It's kind of a vicious circle when you try to mitigate a good building and all of the things to cut down on that heat gain. But even if you don't use an air conditioner and you just wanted to stay comfortable in your building, these are still things to keep in mind, right? How can I stay comfortable without using air conditioning? And I could think about these things about my windows and the different things. So that's solar heat gain coefficient. Window to wall ratio, it asked us to consider our window to wall ratio and how much windows we could have. So the idea behind window to wall ratio is that the more windows you put in the building, the better those windows have to be in order for the building to perform efficiently. Right? So on a building like, say, this one on the far left, where you don't have as many windows, there's more room for insulation or better building envelope assemblies to take place. On the building on the right, though, it's all windows. So those windows better be really good, right, in order for the building to perform just as well as it would for the building on the left. So that's what it's looking at, is window to wall ratio, and telling us, okay, if you're going to build a building with this much windows, they have to be really good. The less windows that you have, the worse windows that you could have. Now to calculate window to wall ratio, it's pretty simple. You just take the gross area of a wall with all of its doors and windows in it. So you take the gross area, including all the doors and windows, just pretend they're not there. What is the area of that wall? Then you go in and add up the square or the meter square, the area of your windows and any glass doors. So regular opaque doors would be considered wall, but if they were glass doors, they would be considered part of your glazing area, your window area. So we're going to take the wall area and then add in the window area. So if you look at an example, I use even numbers, right? So just for ease of calculation. Might not be anywhere close to a reality of a size of anything, but that's just for ease of calculation. So let's say we have a 500 meter, or we have a 1,000 meter square of wall area. That's walls gross area. So we have 1,000 meters, and then we go and we say, oh well, 500 of that is window. 500 over 1,000 is 50%. So 50% of my wall is windows. That's my window to wall area ratio is 50% in this calculation. So that's how you calculate it. And then if you look to see, okay, well, what does that relate to? Well, if I have 50% window to wall area, I have to have a 35 solar heat gain coefficient. Now, the next thing that you find is we've talked about windows and how many of them goes to what kind of windows. Now we're going to talk about shading. So if I have a certain amount of shading on my windows, I can also put in a worse window. Why do I keep saying I can put in a worse window? What's the benefit of putting in a worse window, right? Well, sometimes it can help with the cost of construction because you might be able to pay a little less for a window, but still save energy on your building, right? So you can save on your energy bill. So I'm not trying to, tell you to go put in bad windows. What I am trying to say is there are options built into this code that give you credit for doing good design options like putting in less windows or putting in shading devices over those windows so that you don't get as much solar heat gain in it. And if you are blocking the solar heat or don't have as much solar heat, then you don't have to worry about the solar heat gain coefficient of your window as much. Right? And so maybe you can pay a little less for that window. So this is just saying, let's look at the shading of the window to also give you an adjustment on that SHGC. So it says that for air-conditioned buildings, those are the buildings that we're really paying to cool. Those are the ones we're trying to keep that extra heat out of. Air-conditioned buildings. With external shading, this SHGC can be adjusted. And so it's just letting us know we have an adjustment factor. So what our regular SHGC requirement is out of the table, we can adjust based on the size of our shading that we're putting on there. So what does this look like? Here's our table. This is our table with our window to wall ratio, and it tells us what our SHGC factor is based on what window factor we're putting in, right? So we find our solar heat gain coefficient. Then we go over here and determine what kind of shading we're putting on the window. Now it gives you credit for shading with fins, which is vertical next to a window, or it gives you credit for are you doing shading with an overhang, so horizontal over the top of the window? Which kind of shading? There's two different tables. And so then it asks you, all right, what's your projection factor? How big is that projection? So that we can determine how how much you're really protecting the window so that we can give you your projection factor or your solar heat gain factor. So let's look at how this works. It's not too hard. We look at first, in order to really do the calculation, we probably ought to figure out what is a projection factor talking about? What is that? That's asking us how big is that projection? So projection is A over B, the size of the projection versus the height of it from the top of the windowsill to the underside of the projection. That's B. So A over B. Let's look at an example being if I have a projection that's 30 inches and it is 84 inches from the bottom of that projection to the top of the windowsill, that's 84. A over B, 30 over 84 is 0.36. So my projection factor is 0.36. So when I go back to those tables, I can look at this table here on the right for a projection and okay, I'm 0.36. Well, I have 0.3 and 0.4, so I'm going to round up. So I'm going to go to 0.4 projection factor. And if I have a 0.4 projection factor, I can use my solar heat gain correction factor of 0.19. Perfect. So let's look at the examples that we were using earlier where we had 50% window to wall area that we calculated. If we had 50% window to wall area, we automatically needed a 0.35 solar heat gain coefficient. That's without shading it. But now we come over here and we say that we shaded it. So we can take that 0.35 and multiply it by 0.19 and see that now, since I'm shading my window, I can have a window solar heat gain coefficient of 0.54. There's a huge difference, not just in the amount of heat that comes in, but the cost of that window from a 0.35 to a 0.54. So I can now put in a little bit worse window because I'm shading it and I'm only doing 50% windows. That's what it's looking at, all of it holistically. All right. Now let's talk about window openings. It's a little bit confusing the way that when you read it the first time, so I just kind of want to walk you through it on how to use it. So 4.4.2 tells us that mechanically ventilated and cooled buildings, so you have two different kinds of ventilation. Mechanical ventilation, where you're forcing the air through mechanically, or natural ventilation, where you have openings in the building and it's coming through naturally. So this is telling us, firstly, that if you have a mechanically ventilated and cooled building of occupancies other than hazardous retail and storage, they have to have provisions for using natural ventilation for cooling and fresh air in frequently occupied areas. Now, if we went into the definitions section of this code, there is a definition for frequently occupied areas that lets us know that it's, places that we occupy frequently, not including like closets and bathrooms and hallways and those kinds of things. So frequently occupied areas have to have at least 4% of the floor area being specified as openable windows. All right. 4% of my area has to be looked at as openable windows. So what does this mean? I have, say, 100 meters square, because I use an even easy to use number. I have an area that's 100 meters square. 4% of that floor area has to equate to the operable windows, the openable window. So if 4% of that is 4 meters square, so I have to have 4 meters square in openable window. So I take 4% of the area and then convert that to say that's how much openable window I need. Now, that's for mechanically vented windows, or mechanically vented and cooled buildings. It does say that if you have like a balcony door or something on there, that can be counted in the calculation. Now, what if I have naturally ventilated buildings? So I have this building that has natural openings where the air flows through and I'm not mechanically ventilating it. For those areas, other than hazardous and storage, you have to provide 50% of the window area to be openable. So this one's telling you how much actual area you have to have. And this one is telling you out of the area that you have, 50% of it has to be openable. So this one is just telling me that if, 50% of the area of all my windows total have to be openable. That's in naturally ventilated buildings. So it's just how you read those two sections. It can be a little bit confusing. And it says all the openable windows above ground should be designed with safety measures so that you protect children, have child safety in there. And then windows to any regularly occupied space on the exterior walls in naturally ventilated buildings shall be shaded. What? All right. So what this is saying is, so we went through those calculations for if you provide shading, right? And so this one is saying that we must provide shading. It does talk about windows to occupied spaces. So there may be windows to non-occupied spaces like storage and bathrooms and stuff that we don't have to provide shading for. And it's just those, spaces on the exterior wall. So if I have an occupied space on the exterior wall, I have to provide shading over those windows. So that's just letting us know that there's an extra little thing here of when we have to do it. Now, you could still, because you're providing shading, you could take advantage of that credit that lets you drop to a lower solar heat gain window because you're going to put a shade over the top of it. So make sure you still give yourself credit for that. But that's what it's asking us to do. So let's look at how it's telling us to provide that shading. There are some specifics. All right, so 4.4.3 on shading tells us that for naturally vented buildings of all occupancies, you have to provide horizontal sunshades over the windows, but only on the windows that are south, east, and west. The depth of that sunshade is going to be the height of the window times a factor of 0.234. Right? So it's height of the window times a factor of 0.234. And this figure is directly out of the code. This is the picture taken right out of the code. So how do we look at that? Let's give an example. So if we have a window that's 90 centimeters in length, 90 times our 0.234 gives us a depth of our overhang that has to be 21 centimeters. So the bigger the window, the bigger that overhang is going to have to be. The smaller the window, the smaller the overhang is going to have to be. So it's telling us that we have to, on south, east, and west windows, we have to put this horizontal sunshade. Unless we do these horizontal louvers. So it says you can use horizontal louvers instead of sunshades, but if so, how do you determine what size those louvers have to be? It tells us to take the space between the louvers times the 0.234, and that gives us the size of the louvers. So an example, if I had 18 centimeters between each louver, times 0.234 means each louver has to be 4.21 centimeters in depth. So the more louvers or the closer together I have, the smaller they can be, the further apart they are, the bigger they're going to have to be. All right, so you have those two options on south, east, and west. You have the two options of horizontal being a horizontal projection or these horizontal louvers. But then it goes even further to say we're going to provide, if you have windows on the west, you also have to provide vertical shading, vertical fins. Right? So vertical shading devices shall be provided on the west, the depth of which shall be calculated by multiplying the space, the gaps in between, by the 0.234. So an example, if we had 90 centimeters between these fins, we'd take that 90 times the 0.234, and we'd get that these fins have to at least be 21 centimeters in depth. So this is on the west. So you can see that on the southeast and west, we have to do something horizontal. But on the west, we also have to do something vertical. There are some exceptions. It says the above rule shall be relaxed if it can be demonstrated that shading is achieved by existing neighboring structures. So I have a building next to me that's blocking some of that sunshine, some of that solar heat. I can use that, I can show that, or maybe there's some other structure or something that's going on that's next to me. I can use that. And it also says, of course, nothing is required on the north face of the building. Any windows, any glazing facing on the north face of the building do not have to comply. The solar heat is definitely increased on south, east, and west. South and west especially, west the most. All right, and then your exception. All right, so we've talked about all of the glazing requirements found here in Chapter 4, and so let's talk about now how to verify those requirements. Who looks at all of that, and how do we do that? Most of the time, a lot of the verification on windows comes in at plan review. Right? This is the plan reviewers looking at the window to wall ratio to make sure that that's calculated correctly. So the designer has to make sure that they include those window to wall ratios on the plans. One thing that I find a lot as a plan reviewer is that the designer is not just providing those calculations, so I'm having to go through and do them myself. Well, when you have a lot of other things you have to verify, it gets very time consuming. So what I've started doing is give the plans back to the designer and ask them to show me their calculations for window to wall ratio so that they're doing those and not me. But so plan review is verifying window to wall ratio. Also, a lot of times we're verifying this SHGC, the shading coefficients, the VLTs. We're verifying those up front because a lot of times it's a calculation. Did they use an adjustment for the amount of windows? Did they use an adjustment for shading? And so we calculate those to make sure that they did them correctly ahead of time. But in the field is where those items, SHGC and VLT, become a little bit tricky. Especially for commercial buildings that don't have stickers on the window, and so you don't really know what you're getting. A lot of the stickers that do come on windows from the manufacturer have the U factor, solar heat gain coefficient, and VLT right on them, but commercial buildings, we're not usually buying those stickers from the or those windows from the manufacturer, and so we might get the glass and we might get the frame and put it together in the field, and we don't always have stickers on them. So it is important to verify that they've got the right solar heat gain coefficient and they have the right VLT and things, especially that SHGC, because that's going to play a huge role in sizing that mechanical equipment. On the amount of windows, are they on the north, south, east, or west, and how, what solar heat gain coefficient do they have? Because that Could be a lot of heat making it in the building, depending on all of those factors. So we really want to verify it in the field. How do we do that when there's no stickers on the window? A lot of times what I will do is ask the contractor to provide me their bill of lading or their receipt or something of where they bought their windows that might tell me what those values are, or ask them to get something from their distributor that says, here's what those are. Um, so the burden of proof is on the person doing the construction to provide those values to you, but there's no sense in jumping through all of these hoops of doing all of these calculations, having these requirements, do all the calculations, get it through plan review, and then we don't verify it in the field. So um, it's very important because the mechanical contractor is relying on what those plans say when they're sizing their equipment. And if that's not what they're getting, they could be getting set up for failure on their systems. So it's really important to get those correct. For projection factors and shading, yes, plan review, we're going to look to make sure, okay, how much of that, what was the size of that projection? Did they size that shading correctly and all of that? So that we have the right solar heat gain coefficient number. But there's also a part of that that goes to planning, because a lot of planning departments have very strict specifications, especially from different subdivisions or different areas, on what the building can look like from the outside. The building department is looking at the building and everything, but planning a lot of times said, okay, it has to be this color, it has to have this kind of siding, it has to have these kind of windows, it has to, they have more specifications on what the building looks like from the outside, including what those projections, those shading devices need to look like or can't look like or whatever. So there just needs to be some coordination going on between those two departments to make sure that you don't get hung up on that. Planning approves it first, what the building looks like, before you get into the plan review. That's very helpful, because then by the time you've done the plan review, you know that they're okay with whatever shading devices were chosen. And so that's helpful. When it comes to area of operable window openings, who's doing that? Yes, at plan review, we're going to look to make sure that that area is identified, that they've called out. Is it that 4% of the area? Is it the 50% window openings? Do they have that correct? And then for all of it, it really, really comes down to, on inspections, making sure that they have installed exactly what was on the plans. If you get out there and the projection is different, well, if its depth of projection is different, that's going to change the solar heat gain coefficient that's required, right? And so that's going to change the kind of window that we put in. And so it could have this domino effect. So really making sure that everything is exact per plans. And if it's not, then making sure you go back through that reapproval process to make sure that you have the right windows still in place and all of those things. So it's really important when it comes to windows. It's such a huge role in mechanical equipment sizing that we really need to make sure that once that design gets approved, that the building is actually built to that design. So pretty important. Once we get out of the windows and now we get into the roof, this is our other part of our building thermal envelope that plays a huge role in energy efficiency. And so we get into 4.4.4 that tells us that 50%, at least 50% of the horizontal exposed roof slab of the building of occupancies B, education, C, institution of care, D, healthcare facilities, and E, business. So B, C, D, and E, those occupancies, 50% of the horizontal exposed roof slabs have to be green roof. They have to have a green roof system that manages their water runoff from the rooftops, controls the internal temperatures within the top floors, and helps reduce the carbon footprint of the building. It's nice that they give us the why, that's in there. It does tell us that that 50% area doesn't include covered roof surface like solar panels, solar thermal heaters, machinery, mechanical equipment, that kind of thing. So you subtract that out of your roof area, and then 50% of the leftover roof area has to be covered. So that's how you would calculate. And then it tells us that, hey, when you're doing this roof area, make sure that the structural engineer or whoever's doing that structural design makes sure that they have calculated this green roof and the weight of it in the structural design. And they give a minimum of a 300 millimeter weight for growing medium. So we're looking at making sure that you have this green roof, 50% of your roof area, and it's only required, it doesn't mean you can't do it on other occupancies, but it is a requirement for B, C, D, and E occupancies, and that you've designed for it structurally. Another thing that they say is to just, make sure that you have accounted for how you're going to deal with the moisture, that the plans come in and they tell you, how you're going to make sure that the moisture doesn't get into the building. What are those different control layers to deal with drainage and moisture? So provide something like that in the process. And then another thing that it talks about is, it's only required on 50% of the roof area. So what do you do for the other 50% or whatever? So it says wherever there's not that green roof, you need to go ahead and provide some insulation. To give you the green roof will provide some insulation. So wherever there's not green roof, that we need to go ahead and provide some insulation on that. So to cut down on that transfer of heat. So these are great requirements. They're dealing with the carbon footprint of the building. They're dealing with the energy efficiency of the building. So there's some great things going on, the temperature of the building. How do we verify this? What needs to be verified? There's a couple different processes in place probably here. Definitely at plan review, looking at, does the structural design, is it adequate for this roof? Do they have their 50%? Did they account for the insulation? Did they account for their control layers? And then, of course, on the green roof itself, you're going to get into the fixtures, the plumbing, there's all kinds of things involved here. The majority of this will be building department type inspections and plan review. That's the envelope. We've talked about the site. We've talked about the envelope, the things that are considered to be the major parts of the envelope. And now we're going to talk about the systems inside the building. Look at the requirements for daylighting, lighting power densities, occupancy sensors, fans, elevators, escalators, renewable energy options, and the big one, HVAC systems. Now, while the envelope provisions told us what kind of window we had to have based on the amount of our window to wall ratio, this section tells us how to treat the light coming in those windows and set a minimum of how many windows we actually have to have. So we saw earlier, depending on how many we have, here's what kind of window you have. This section is going to tell us how much windows we actually have to have. So it says that window area shall not be less than 14% or 1/7 of the total floor area, not the wall area, the floor area of the building. So if I have the 14% of my floor area equates to my window area, right? So that's what that's trying to tell us. Now, it also goes on in 4.5.1.2 to tell us that every regularly occupied space, that's again a defined term, so you can look that up, shall contain a minimum percentage of daylit area along the building perimeter. And so we have no window less than 1 meter square to ensure that that light can come in, and so that then that we can comply with the rest of the provisions that we're getting ready to talk about. So this is telling us one thing about how much area has to be windows. Then it goes on to say that each of those minimum window area of 1 meter square, we cannot have less than that, even if our floor area was smaller and called for less than that, right? So it says for rooms that measure less than 8 feet in depth, the window area shall be at least 20% of the area of the external wall. So maybe this is the external wall. So for 20% of the area of the external wall is what your window area has to be. Now, if your room is between 8 and 14 meters depth, then 30% of that exterior wall has to be windows, and rooms greater than 14 feet depth, 35%. So this is, the bigger the window, the more area of window, or the bigger the room, the more area of window you have to allow more lighting. The deeper that room is, the more window area we need to allow the light to come in. Now it talks about some daylighting requirements also here coming up, but it's important to understand these requirements before we can move forward, because this is telling us how much windows we have to have. So how do we use windows to even save energy? Here's kind of how it works. If enough daylight's coming in the windows, then we don't need as many lights on inside that space. So we need to use the free light that's coming in whenever we can. But how do we control that? And what happens when it gets dark out, or a cloud comes over, and or something happens to block the light from coming in? What do we do? So this is where we use sensors and controls to keep a certain level of light in that space. So 4.5.1.3 says for building of occupancies A5, hotels and lodging houses, B, education facilities, C, institution of care, E1, offices, and E2, research and testing labs. For those occupancies, photoelectric sensors shall be connected to luminaires to enable dimming or switching off lamps that do not require to be operated because of there's adequate daylight. Right? And so it says that the photoelectric sensor shall be located approximately half the depth of the daylit zone. Let's go to the definitions section in this code to find that a daylit zone is an area with a depth of 5 meters parallel to any glazed external wall. So we have this wall, and for 5 meters parallel to it, we have this daylight zone. We need to put our controls halfway into that zone. That's what that is telling us. And then it says if occupancy sensors are installed in that daylight area, the occupancy sensors shall override the daylight sensors during non-occupancy period. So I have a room. Maybe it requires an occupancy sensor. It's a conference room or something, and it requires an occupancy sensor. But I also have this daylight sensor that's sensing how much daylight, which one prevails. The occupancy sensor. There's no reason for that daylight sensor to be turning the lights on and off if nobody's in the space. So this is telling us that it wants that occupancy sensor to overrule the daylight sensor. This brings up a good point for we're kind of testing those controls. When you have, you usually when we're verifying that things work and they don't work, we look at the daylight sensor. Does it work? Yes. We look at the occupancy sensor. Does it work? Yes. But are you looking to see that the occupancy sensor and the daylight sensor work together? That occupancy sensor truly is overriding and keeping that daylight sensor from coming on. A lot of times what happens is we don't look at how they work together, and so they fight each other and no energy is saved. So just something to keep in mind. There are some exceptions. Zones with special requirements are exempt from the stipulations, but the designer has to justify the reason. Why do you think you need to be let out of this daylighting requirement? And then it says, because this does apply to hotels and lodging houses, it says the individual hotel rooms are exempt from the daylighting requirements, but all the other spaces in the hotel are not. All right, lighting power density. How much light wattages can we put in our spaces? This is broken down by the type of space. Right? The type of space will tell us how many watts per square foot we can have for each of those spaces. So it's set in this table. It's provided for the respective functions with all the building occupancies. So if we give an example, if we have an office building and it's allowed 9 watts per square foot, and say I have 100 meters floor area, right? So 100-meter floor area would say that I could have 9 watts per meter. I could have 900 watts in that area. If I could do it by each individual area, or I could do it by the whole building. So maybe I have 1,000-meter floor area, then I have 9,000 watts for the whole building. I might have mixed occupancies, so I could say, how much of the square footage is office, how much of it is educational, how much of it is parking. So you could calculate it each separately that way. But that's how you use that. And then it goes into another section that says, in addition to thinking about this lighting power density, we want you to think about the illumination values, the lux, as specified in Table 815 to 814 or 8114 of Part 8 of the code. I don't like to jump around between a bunch of things, but I want us to kind of handle that right now instead of later. So we have to think about the power density, but it also is going to send us, it's giving us a pointer over to Part 8 of the code to provide for the building, for the lux of the lighting. So let's just look there real quick. It just has a bunch of tables based on occupancy that's letting us know what that illumination level is for those different applications. So it has provisions for recommended illumination values, stating that the recommended value of illumination required for the building of different occupancies based on the activity are here. And then it wants you to have the initial illuminance should be higher than that recommended value, because after those lights have been in there for a while, that illumination level is going to drop a little bit because after just the lights being there for so long. So it's asking, here's the illumination levels that you need to have in these different areas, but maybe start a little higher than this, because over time they're going to fade. And then it's also talking about gradual transition rather than a sudden change. So eye adaptation, it's asking us to keep that in mind too. So a gradual transition of brightness from one portion of the building to another within a field of vision is recommended to avoid or minimize glare. Where I see this come into play a lot of times is maybe if you go from outside and you're going into a parking garage where it's really light outside and you're going into a parking garage, and now the light is a lot, the light levels are a lot different. You have eye adaptation issues. So it's asking you to look at those two, to look at the illumination levels into the different spaces to make sure that the levels provide a a gradual transition instead of a big huge change. So it's asking you to keep that in mind. So that's all. That's why it's sending us over here to Volume 3, Part 8, to look at those illumination levels. But let's get back over into Chapter 4 and keep going with the energy provisions. It tells us in 4.5.3 that we need occupancy sensors, right? It says that in order to limit the use of electricity in the unoccupied areas of the building, occupancy sensors are linked to the lighting, except for emergency and security lighting. They shall be installed in the public areas of the buildings of these occupancies. The E's, A5, A3, and B's, office, hotels, apartments, and education. The public portions of the building, so it's applicable to meeting rooms and corridors, covered parks and corridors in those occupancies. So we need occupancy sensors. I love this code so much because it tells you not just what the requirement is, but why. In order to limit the use of electricity in the unoccupied areas of the building that are linked to the lighting, we're going to provide these sensors. That's great. That's nice to know that that's why they want you to do it, not just because. So it does go in to say that if you have car parks, so in your apartments and your educational where you're required to put your occupancy sensors, if you have, for car parks, a minimum of 2/3 of the lighting has to be controlled by occupancy sensors. And then it goes further to just say that the emergency lighting cannot be on occupancy sensors in any of the buildings. All right, so we've talked about a lot of those lighting, daylighting type of requirements, and now let's talk about who looks at them, because this can get a little bit confusing and gets missed a lot of times. I think we've mentioned it a little bit early on, that when it comes to lighting requirements in an energy code, a lot of times those types of items, we might check them really thoroughly at plan review, but a lot of times they get missed in the field. Even often it gets missed at plan review, and that's because we can't decide whose job it is to look at it. Do you have like an electrical plan reviewer and electrical inspectors, and then you have maybe a building plan review and building inspection? And who looks at this? A lot of times the electrical folks are looking at only things that are in an electrical code and not a building code or an energy code. And so a lot of times the building inspector is saying, hey, this has to do with electricity. I'm not looking at it. The electrical guy is going to look at it. But the electrical guy is over there saying, hey, this is in the building code. It's in an energy code. It has nothing to do with my electric code. I'm not looking at it. And so many times nobody's really looking at it. So who's verifying that? So a lot of times we have to come up with some policies ahead of time and identify and get agreement on who's going to look at it on plans and who's going to look at it in the field. Because it really is important, like we talked about a minute ago, especially on those sensors where they could fight each other, and we don't know who's looking at what, and or if it's being looked at all. So we really want to make sure that we're identifying that. So whoever's looking at it, on plans, of course, is going to verify the area and the size of the glazing required. Remember, we have those requirements for depending on the depth of the room, on the amount of glazing that has to be included and that size, minimum 1 meter square, those types of things. We can verify those on plans pretty easily. Size of daylight zones. This is something that I almost always, as a plan reviewer, have to send the plans back to the designer and ask them to identify those daylight zones. Otherwise, I'm spending a lot of time going over my plans, measuring the daylight zones next to all the windows and figuring out if I have enough. It's really up to the designer to specify on the set of plans that here's my daylight zone. Yep, I've accounted for it. And oh, that control, that daylight responsive control that's supposed to be halfway in the middle there it is. And this is the location. That really should be called out on the plans. And so that all we have to do is verify it. And on the plans, we're looking at, okay, where are those occupancy sensors? There's certain occupancies that require them and only in certain spaces. And so are those being met? Is it in the parking garage? Is it in those, those public areas, whatever that requirement was? And so making sure that on the plans, it's calling that out. Are they using the right lighting amount, and they're not putting in a ton of lighting? If they're an office and they're only allowed that 9 watts per square foot, are they sticking to that number and using that? And so just making sure that they're getting that. That's a lot on plan review. When it comes to field inspections, again, it comes down to just verifying what got approved on the plans, because if something's different in the field than it is in the plans, then we have to go back and say, okay, they didn't put in the right amount of windows, or they don't have a daylight zone there, or they don't have their occupancy sensors where they're supposed to, or whatever. It could change things, and we need to make sure that we stay in approval as we go. Any changes in the field would need to go back through and make sure that they still are complying with all the other requirements. Again, a domino effect where one thing out, if I don't have the right daylight zone area, then is that occupancy sensor in the right place, or is that daylight responsive control in the right place? Do I have the right size of windows? Do I have the right amount of windows on that exterior wall? So making sure that those are correct. Not asking inspectors to go out in the field and count light bulbs to make sure that they're meeting their lighting power density. But a lot of times what I will do as an inspector is go and do, spot checks. I'll go into a room and maybe look at the lighting and see, do they have the right lighting? And if so, I'm not checking every single light bulb in the building. But if I start seeing that they're off in 1 or 2 rooms, then I'm going to go back and say, okay, I'm halting this inspection. I'm seeing that your lighting is not complying, and we need to get some compliance out of this lighting. And so you can often do spot checks without looking at every single light bulb in the building. It's more so pretty much if I, as an inspector, if I have to pick my battles, I don't have a million hours to do inspections. And so I have to pick my battles sometimes when I go into the field. And so a lot of times I will look to see that the lighting nowadays is pretty efficient. And so they're probably not, unless they're putting in double the amount of light bulbs that they were supposed to on the plans. I'm more worried about the controls, right? The light bulbs are efficient, but shall we shut them off when we don't need them? I'm going to, if I have to choose between lighting power densities and controls, I'm going to go after the controls to make sure that they're shutting them off when they're supposed to. The controls aren't fighting each other. They're in the right places. They're in the right rooms. That there's the ability to turn lights down, dim them, save energy somehow by actually turning them off. If I have the extra time, then yes, I will do my spot checks on the lighting power densities as well. But so that's just kind of how I handle plan review and inspections of lighting and day lighting. It is important. It does go to quite a bit of that energy use of a building, so of course that's why it's called out here. So we just want to make sure that we're looking at that. All right, 4.5.4, ceiling and wall mounted fans. So this is going to tell us about naturally ventilated buildings. So those buildings that are getting that natural ventilation through natural openings like windows. And it only applies to occupancy A, which is residential. So for naturally ventilated residential buildings, ceiling and wall-mounted fans have to be provided in each regularly occupied space. So residential buildings that are getting natural ventilation and not mechanical ventilation have to have a ceiling or wall-mounted fan in each regularly occupied space. Keep that air moving, right? For other buildings, for buildings of occupancy B, education facilities, C, institutional of care, D, healthcare, E, business, and I, assembly, the ceiling and wall mounted fans shall be provided in each room more than 25 meters square with a minimum of one fan every 25 meters. So if I have a larger room, 1,000 meters, then I'm going to have a few fans, one every 25 meters. Okay, so there are some exceptions of not needing them in corridors of buildings of any occupancy or in intensive care units, critical care units, or operating rooms in hospitals or clinics. So try to get those fans in there, get that air moving, get that ventilation going. We're going to talk more about ventilation in a little bit. In 4.5.5 talks about lifts and escalator efficiencies. So there's ways to save energy in buildings that have elevators and escalators. For escalators, we see in section 4551 that in buildings of all occupancies, they have to be fitted with, if there's an escalator, it has to be fitted with controls to reduce the speed or stop it when no traffic is detected. And so there's a couple ways to do that. There's some energy features, and it gives you a couple. One, reduce speed control. The escalator shall change to a lower speed when no activity has been detected for a period of up to 3 minutes. And detection shall be a photocell activation at the top and bottom landings, or the use on demand. The escalator shall shut down when no activity has been detected for a period of up to 15 minutes, designed with energy efficient soft start technology. That's, it takes a lot of energy to start and stop things. And so it's saying use that soft start technology that gets it going. Might be a little slower, but it doesn't use as much energy. The escalator shall start automatically when required, and activation shall be photocells installed at the top and bottom of the landings. We're going to see in a little bit how this ties into a different section of the code. It's kind of, it has the same requirements, maybe goes into a little more detail later on, but they tie in together. When it comes to lifts, to save energy in elevators, lifts, section 4553 lets us know that the elevators, the lift in the buildings of occupancies, all of these, the hotels, medical facilities, offices, research and testing labs, small shops and markets, large shops and markets, large assembly with fixed seating, large assembly without fixed seating. Right? So in all of these occupancies, they have to the elevators, if there's elevators, they have to be provided with controls to reduce the energy demand using using certain features if it's a traction drive elevator. So it has to have an AC variable voltage, variable frequency, VVVF, drive on non-hydraulic elevators. What in the world is that? So VVVF, variable voltage, variable frequency. It's a lift drive that employs frequency inverter technology, which regulates the input voltage and the frequency throughout the whole journey on the elevator, drawing a lot less current during acceleration and deceleration. When compared with other modes of drives, the VVF drive offers low starting current, high power factor with good ride quality and floor leveling. It can reduce motor starting currents by as much as 50 to 80% compared to conventional motor drives. So further, the wear and tear of the equipment can also be less during start and stop of the motor that's using the VVF drive. It takes a lot of energy if you think about it. So you have this lift, and it takes a lot of energy to get it going and a lot of energy to stop it, that braking horsepower to stop it. And so anything that you can do to cut down on those on that energy consumption, and these VVVF drives do that. So it's telling you you need to use those. And it also says on elevators, high efficient lamps with provisions for switching off when the lift is inactive for a period of up to 5 minutes. And then the provisions to operate in standby condition during off-peak periods when the lift has been inactive for at least 5 minutes. So again, we're going to see how all of this ties in later on with some other provisions in the code. Section 4.5.6 brings in some renewable energy options. So there's options, but they're requirements. Right? So they're different for residential than they are for all the other occupancies. So 4.5.6.1 tells us that buildings of occupancy A, those residential occupancies, have to have solar or other renewable sources of energy to power 3% of the total electric load of the building. So for residential, need to provide solar or other renewables to power 3% of the total electric load for that resident. Now, when it comes to all the other occupancies outside of residential, it says you provide solar or other renewables to power 5%, but only 5% of the lighting and the fan loads is what we're looking at. So different than residential. 5% of the lighting and the fan loads of the entire building. And then it says for all occupancies, the solar or the other renewable connection shall power spaces in the following order. And it gives these order of how we want to see things going after the lighting. So lighting in underground basement or underground or basement spaces, dark corridors, supplementary lighting, fans, emergency lighting like for the stairs and the egress stairs, emergency signs, egress path lighting, that sort of thing. Kind of placing a priority on what those go after so that you're really keeping safety in mind when you're doing the renewables for your light to power some of your lighting loads. So again, residential, 3% of the full load of the building, full electric load of the building. At all other occupancies, 5% of the lighting and fan loads of the buildings. So who do we look at for verification of this? You know, that comes in a couple different, there's electric, so maybe your electric plan reviewer, your electric inspectors. There's building, because do we have, are the loads calculated to hold this? If the solar or the renewable is on the building, has it been calculated to hold that? There's a lot of times planning that comes into play to say, did the planning department approve where these things are located? Does it look right? Because it is on the outside of the building. So there are different departments that come into play. Making sure you communicate between all departments, because a lot of times, again, you don't know that maybe if it's planning involved, they're not engaged in this building energy code all of the time? They have their planning requirements. Do they know that there's these other requirements? Do we really need 3 inspectors looking at it, or can we come to an agreement on, all right, the planning guy is going to look at it for this, but could he also look at it for this and this? Or will planning turn that over and say, okay, you're going to go look at it for structure and you're going to go look at it for electric. Can you just also make sure that they put it in the right spot, or that it matches the design, or whatever planning's requirements are for it? So just kind of working together to cut down on the number of inspections, and to also make sure that everybody's covered for all the different requirements. So that's just something that we look for on renewable energy. All right. So now we have gotten to our HVAC system requirements. Usually that's a big, huge set of complicated requirements, but right now in the energy efficiency chapter, chapter 4, all it does is give us a pointer. And it says that in 4.5.7 under HVAC systems, hey, you need to go over to volume 3, part 8, and look at those requirements over there for the energy efficiency of HVAC systems. It has its own chapter just for energy efficiency of HVAC systems. So this section is really short and sweet in chapter 4, telling us, hey, go over here and do what it says there. So we're going to do that in a few minutes, but I just want to finish up real quick in chapter 4. So 4 talks now, we've looked outside the building, we've looked at the building, we've looked inside the building, and now we're going to look at water management. What do we do to manage the water and conserve water and deal with water? So this section is going to talk to us about gray water, efficient fittings in our restrooms, our toilet rooms, and service hot water and pumping. So let's look at that. First, the reuse of gray water. So this tells us that for buildings of occupancy A5, hotels and lodging houses, E1, offices, and E2, research and testing labs, they shall reuse the gray water for water efficiency and management. You have to use your gray water. What that's saying is gray water from the wash basins shall be reused in toilet flushing and or irrigation after the filtration to ensure that a BOD, a biochemical oxygen demand, level of less than 50. Such water shall not be considered potable. So this is saying in those occupancies, take that water from those wash basins and use them to flush your toilets or irrigate the land after you've treated the chemicals, and then such water shall not be considered potable. You can't use that water for drinking or cooking purposes. Efficient fittings in toilet rooms. So water efficient fittings, including faucets, shower heads, flushes that use less water for the same function as effectively standard models, shall be used in buildings of all occupancies. The low flow fixtures shall be in accordance with this table 3.4.7. So all occupancies have to include low flow fixtures, or efficient fixtures, right? From your urinals and water closets, showers, and faucets. And it gives you what those requirements have to be for each of those different fixtures. Then you have service water heating. So again, I like the fact that it tells you why. In order to reduce the energy used for hot water, for heating water, buildings of occupancy D1 and A5, medical facilities and hotels, the 2 occupancies that probably use the most hot water, right? In order to save energy for using all of that hot water, or for heating all of that hot water, those occupancies have to use solar hot water system to supply a minimum of 30% of the total building hot water requirement. The solar water system can be flat plate solar collectors, like here on the left, or vacuum tube solar collectors like here on the right. This system has to be designed and installed with a backup system or as a preheating for the main hot water system. So if you're in one of these occupancies using a lot of hot water, you need to use some solar thermal, some solar hot water for at least 30% of that water heating load. All right, that is it for chapter 4. So those are our energy efficiency requirements. They covered a lot. They covered outside the building, inside the building, the systems inside the building. So there's a lot that it covered, water, everything. And so pretty good. But now if you were just looking through the Bangladesh Building Code, you would see energy efficiency comes up in a lot of different places, and conservation comes up in a lot of different places. So we're going to look at some of those places, and we're also going to go back and look at those pointers where it sent us to another place so that we can see what all we need to comply with. It's not all just under that energy efficiency chapter in chapter 4. So let's start with volume 3, part 8, chapter 2. Remember where we got that pointer, go over here to find all the HVAC requirements, the energy efficiency requirements for HVAC, heating, ventilating, air conditioning. So when we go over to those requirements, the first thing we read in the chapter is the chapter's purpose. And so the purpose of the chapter is to provide minimum standards for regulating and controlling the design, construction, installation, quality of materials, the location, operation, performance, maintenance, and use of air conditioning, heating, and ventilation systems to ensure acceptable conditions of air inside the building that are required for human health, safety, and welfare with energy conservation. So we see energy conservation as a main objective when we look at the sections about the design and the materials that make up all the systems. Now, when we get deep into this section, it's going to go into, the design of our building and how the design of our building has a lot in determining what equipment goes inside of that building. So when we talk about designs, I think it's great that the very first section, 2.6.1.4, I think its title pretty much says it all. This is the longest title. The title is Design Air Conditioning, Heating, and Ventilation System, Taking Consideration for Energy Efficiency and Energy Conservation. So it's letting us know that we're going to go after energy efficiency and energy conservation in our design of the air conditioning, heating, and ventilation system. So in that section, it tells us to provide data to the design architect to keep the provisions in the building for reduction of energy usage required for operation of the air conditioning system. We have to optimize the design by coordinating the design with the architect at the early stages. And it says that the schematic design in the schematic design phase and continually improve the design during the design development process. Right? So what is it telling us? It's telling us that the designer of the building and the designer of the equipment, they better get together. They're going to talk. They're going to need to work together because the design of the equipment, it has to rely on the design of the building, and we need to do that, and you need to look at that throughout the whole process from start to finish of the design before it gets constructed, to keep talking. So what are those things in the building design that can help optimize the design of the HVAC equipment? A lot of things we've already talked about, right? The number of windows, the solar heat gain coefficient of those windows, the shading of those windows, what kind of roofing material? Do we have a light roof that reflects heat? Do we have a dark roof that absorbs heat? Do we have a vegetative roof? Do we have a green roof on there? Is there roof insulation on there? All of those things on the envelope, plus the type of lights, right? Are we using efficient lights, or are we using older lights that put off a lot of heat? Some of those older lights, especially like in can lights and things, they put off a lot of heat. And so what kind of lights are we putting in? How many lights? Are we using renewables? How many people are in this, going to occupy this building? What is it going to be used for? How much equipment is going to be in that building? There's all kinds of things that go into designing the right equipment. But when we're just talking about the building, what is that envelope made of, and what are the other systems inside the building that we need to look at? There are a lot more things that go into optimizing the design, but those are some of the things that we've already covered. We're going to go, we're going to look at all of that a little bit more in a minute, but if you think about this, these are things that could determine how well that piece of equipment runs, what size it has to be, right? Maybe if I design my building good, and then I can put in a smaller piece of equipment. And that smaller piece of equipment, which is going to cost me less, is going to run efficiently. And now I have saved money on not just my equipment, but my energy bill. So there's a lot that goes into that, and this code is making sure that you take all of it into consideration. It also is going to ask you to look at the orientation of the building when you're designing your mechanical equipment, so that you are giving yourself, you're giving credit to the system for which way that the building is faced. The effective orientation of the building and arrangement of rooms or spaces shall be analyzed in the planning stage of the building to find out the most effective plan of the building in terms of building use, application of air conditioning, heating, and ventilation system, and the reduction of energy consumption. What did that just say? It didn't just say that we have to look at that for the building, for the mechanical system, but it says in the early stages of the design of the building, we need to try to plan the building to be at its optimal orientation. And then we take that orientation and we put it into the design of the mechanical equipment. And then it's talking about our shading. So building design and use of materials. Analysis shall be carried out in the design stage for selection of the appropriate shading devices and other materials as set forth in this section, so to take advantage of the reduction in energy consumption related in air conditioning, heating, and ventilation systems. Selection of glazing materials shall be in compliance with Chapter 2, or with Section 2. So it's telling us early on when we're designing the building, we have to just, put in as much thought as we can into what windows, how many windows, the kind of shading that we have, and then all of that so that we optimize energy efficiency of the building. And then all of that has to be considered once we are designing the mechanical equipment. So pretty good ideas there about that. And then it goes in further. So within the HVAC requirements, there's this complete energy conservation section that covers all the provisions for energy conservation measures when designing your HVAC system and installing them. So we're going to look at each one of these, the design parameters, how the system design, the controls, balancing. We're going to look at all of this real quick. All right, so first things first, general section is specific to say that air conditioning, heating, and ventilation systems of all buildings shall be designed and installed for efficient use of energy. The calculations for cooling and heating loads shall be based on data which leads to a system with optimum energy use. So calculate those loads based on where the building's being built, how it's being built, how it's being used, all of those, the different materials, all the different things to determine what piece of equipment needs to really serve that heating and cooling and ventilation load. If we build the building good, we maybe can use a smaller piece of equipment, right? Bigger is not always better. And so that's what it's asking us to look for. It does, however, specify that the general standards of comfort or particular environmental requirements within the building shall not be sacrificed in an endeavor to achieve low consumption of energy. For special applications such as hospitals, labs, thermally sensitive equipment, computer rooms, and manufacturing processes, the design concepts and parameters shall conform to the requirements of the application at minimum energy levels. What this is telling us is that I'm not going to just do anything. I'm not going to freeze people out or overheat people just to save energy. I have to keep comfort, environmental requirements. They can't be sacrificed just at the cost of energy efficiency, right? Oh, I'm just not going to heat the building at all. That way I save a lot of energy. No. And then it says, for those special applications, the hospitals, labs, and things like that, there are times when energy efficiency is on the bottom of the totem pole when we're talking about what the requirements are for some of those places. The design concepts and the parameters they have to look at the minimum energy levels because there might be other things that overrule that. What are those design parameters? So, we say we got to design the system so for where we're building the building and how we're building the building. So, there's, of course, we're going to have to take into consideration the design. What are the outdoor temperatures for where we're building this building? What are the inside temperatures? This code says you have to use an indoor design temperature of not less than 24 degrees Celsius for cooling, unless something else pops up. But so you have outdoor design temperatures, and there's a bunch of tables that show you how to figure out that value. You have indoor design temperatures, then you have relative humidity that you have to figure out. So there are some tables in there to calculate, to find that range of relative humidity. And then, so those are some things that go in there. And then we all, like these, find these all too familiar tables on solar heat gain coefficient. So this is pretty much the exact same tables that we already looked at to say what is our window to wall area and what solar heat gain coefficient do we have to include in the design for our mechanical equipment. We did it for the building. Now let's consider that for the design of our mechanical equipment. So it gives you, how to look at what's your solar heat gain coefficient based on your window to wall area, and what's your solar heat gain coefficient with those adjustment factors based on what kind of shading you did. So those exact same tables, same way of calculating, same everything got brought over here so that we make sure that we're looking at that. Another thing it says on system design is that we're going to look at different ways of load variation. So consideration has to be given to changes in the building load and the system designed so that maximum operation efficiency is maintained under part load conditions. What is that saying? It's saying sometimes I'm not operating my building full bore, so I have to be able to, my system has to be able to operate and have controls to operate in part load conditions. The total system shall be separated into smaller zones having similar load requirements so that each zone can be separately controlled to maintain optimum operating conditions by reducing waste of energy. So in this example here, we have this building that has different uses. So it's saying you break the building up into zones of like uses. So maybe this is an office and this is a warehouse, right? I'm not going to heat, cool, or ventilate the office space the same way that I do the warehouse. So I need to have them on separate zones, heating and cooling separately instead of one big huge building that's just overall heating and cooling the whole building the same way when it doesn't need to be. I might not provide very much heating in my warehouse or a lot of ventilation in my warehouse, depending on what I'm storing. But I need more in the office for comfort and for fresh air. So I'm going to zone them so that I have a thermostat here and I have a thermostat here, and they are controlling things separately. Then it also says that to bring in energy recovery where possible. Not a requirement. It's just saying, I mean, it's not mandating that every occupancy do it or anything. It's just saying where possible, energy recovery systems shall be adopted. So who determines that? Maybe the building department. When you apply for your permit, they're going to say, hey, it's possible for you to put in a ERV. Why don't you do that? What is the benefit of that? When I have to ventilate a building, and a lot of buildings require a lot of ventilation, especially commercial buildings, assemblies, and offices and those kind of things. They require a lot of fresh air based on how many people are in the building. And so I'm bringing that fresh air into the building, and it's coming in at whatever temperature it is outside. So if it's 100 degrees outside, I'm bringing in 100-degree air, and now my air conditioner has to offset that. Right now it has to work harder. The whole idea here is to keep that equipment from working very hard. And so what an ERV does is it brings that air in from outside, whatever temperature it is. If it's hot air, then it brings it in from and takes it across the heat exchanger, it pulls the heat off and delivers a colder air into the building. So now my air conditioner doesn't have to work so hard. In the winter, it takes that cold air from outside, runs it across the heat exchanger, and brings a warmer air, picks up warm air, adds it to it, and brings it into the building. So you're tempering the air that comes into the building a little bit more and don't have this huge change in outside temperature to inside temperature that your mechanical system has to make up. It also, the nice thing about an ERV also, when it runs across this heat exchanger, it also deals with moisture. So if it's humid outside, it can remove some of that moisture in the air before it delivers it into the space. So again, required where possible. All right, equipment and controls. So this section 212.4.1 and 212.4.2 talk about air conditioning, heating, and ventilation systems shall be equipped with devices and controls to automatically control the capacity of the system when the building requirement reduces. Okay, so this is telling us that the control system has a device to reduce energy use considering the effective building energy storage. So looking at part load controls and sequence of operation. What is this talking about? This is talking about not cooling with outside air. Sorry. This is talking about controls to reduce the amount of energy used when the building isn't requiring all of the load be used. So if I have a building and it says, okay, in order to heat or cool this building, I'm going to need 4 boilers. So I have these 4 pieces of equipment that would require at the worst load conditions possible, it would take all 4 of them to supply the building. But we're not at worst case scenario all the time, right? So there are times when maybe we're closed and we don't need very much heating or cooling, or maybe there's not very many people in the building, or it's a holiday, or maybe there's certain hours that are busier than others, or there's certain parts of the day where there's more heat coming in from the windows than other parts of the day, or whatever the situation is, it's very rare that 100% of the time that building is at worst case scenario, right? There are times when it's not. And so it wouldn't take all 4 pieces of equipment to serve the building. So what it's asking us to do is to provide these controlling sequences and controls that allow us to, when the load calls for one, to only have one going and not all 4 of them. When the load increases and now we need 2 of them to serve that load, then 2 come on. And maybe we get up to 3, and maybe we get up to 4. But as soon as the load reduces, we're back down. We're back down. We're back down, right? So it's asking us to really pay attention to control systems to reduce the energy use for when the loads call for it. And that's a lot done through sequence of operation, part load controls, and that sort of thing. All right, now we're going to talk about cooling with outside air in 212.4.2. This is telling us that each air handling system has to have the facility to use up to and including 100% of the air handling system capacity for cooling with outdoor air, and to do it automatically whenever the outdoor air will result in a lower usage of energy than would be required under normal operations of the air handling system. So what that's telling me is maybe I'm using an air conditioner to cool a building to 75 degrees. But outside, the temperature has changed. And now the temperature outside is 70 degrees. Why am I paying to cool the air to 75 when the temperature outside is 70? I need to find a way. What are the controls that I can use, or the methods that I can use to shut down this refrigeration system or whatever it is I'm using to cool, that's using a lot of energy, takes a lot of energy to cool a building. What can I do to shut that down and bring in the outside air? Use that outdoor air to cool the building. A lot of people see it as an economizer, but there are other ways to do it. And so depending on what kind of mechanical system we have, what am I doing to use the outside air when it would be more efficient to do so? Now, there are some exceptions. There's an exception, cooling with outdoor air is not required if the air handling system capacity is less than 2,500 liters per second, or the total cooling capacity is less than 40 kilowatts. Where the quality of outdoor air is poor, so that it would require too much treatment of the air. Maybe there's a fire outside, or maybe it's just a bad air quality day. You don't want use that air, so that would be an exception. Where the need for humidification or dehumidification requires the use of more energy than is conserved by using the outside air. So if I bring in all that outside air and it has too much moisture in it, and it's going to cost me way more to dehumidify than it would to just run the air conditioner, then I don't have to do that. Or where the use of outdoor air cooling would affect the operation of other systems, so to increase the overall energy consumption of the building. Would it make other systems run harder or something? So we'll talk more about economizers in a few minutes. All right, let's talk about mechanical ventilation. So sometimes we don't open our windows, or maybe we don't have a lot of operable windows to open. So we provide ventilation mechanically to ensure that we always have a flow of fresh air moving through the building. Air is important. It's a requirement. And different occupancies require different levels of ventilation. That's all found in like the mechanical code section. This right now we're talking about energy efficiency, but the mechanical code will tell us, okay, which occupancy requires how much fresh air being brought in. But why do we need that fresh air? There are a lot of reasons that we need a constant flow of energy or of air, or at least an intermittent flow of air. But in commercial buildings, we have more of constant flows. So we need that air moving through there to do things like keep condensation down, right? You see condensation on your windows, you don't have enough air moving through your building. So it keeps condensation down. It keeps people healthy. It cuts down, it removes pollutants. So we often associate pollutants with outside buildings, but there's also pollutants inside the buildings, things that, the paints and the finish material and our furniture, they all might be off-gassing or whatever. So we have these pollutants inside of our building. So as long as we have this fresh air circulating, what goes out must come in, so you have air going out, you're bringing fresh air in, and you have this transfer of air going on to keep the building healthy and the people healthy. So when you have, it says for mechanical ventilation, each mechanical ventilation system shall be equipped with a readily accessible means of either shutoff or volume reduction and shutoff when ventilation is not required. Then you have automatic or gravity dampers that close when the system is not operating, have to be provided on your intakes and exhausts. So I'm going to make sure that I have my ventilation system, but there has to be an auto shutoff. So if, again, there's a fire outside, I don't need all that smoke in my building, I'm going to shut off my ventilation system for a little while. And then anywhere where I have an intake or an exhaust, I'm going to have a damper, whether it's automatic or gravity, depending on what the mechanical code would require me to have. Those dampers have to close when I'm not exhausting or being required to bring in air. All right. Efficiencies of our equipment, yes, we're going to always have a minimum equipment efficiencies. The older equipment didn't run quite as efficient as the newer equipment, so we have these tables in the code that tell us, depending on what kind of equipment, what kind of efficiency it has to be, what coefficient of performance or integrated part load value, lovely terms that we have to learn when we're doing mechanical systems. So what efficiency do we have, and according to what test standard? So then it says, okay, if you don't find your piece of equipment in here, then to go to ASHRAE 90.1 to find what the efficiency of that equipment should be. For controls, it goes further. I always say mechanical code has control issues, right? It just wants, it's not going to override whatever the mechanical code itself says, but the energy portion for HVAC is telling us, okay, you have to run these systems, but let's provide controls to run them as little as we possibly can or as efficiently as we possibly can. So we're not going to tell you you can't run your systems. We're just going to ask you to, shut them down when they're not needed or turn them down a little bit whenever you can. That's what we're looking at. So a lot of the HVAC requirements when it comes to energy efficiency have to do with controls. All mechanical cooling and heating shall be controlled by a time clock. It can start and stop the system under different schedules for 3 different day types per week, capable of retaining the program if the power goes out for at least 10 hours, and includes an accessible manual override that allows us to run the system for up to 2 hours without being on the time clock. Then there's some exceptions. Cooling systems less than 8 tons or 28 kW, or heating systems less than 7 kW or 2 tons. don't have to have that time clock. All heating and cooling system equipment shall be temperature controlled. Where a unit provides both heating and cooling, controls have to be capable of providing a 5-degree deadband, a 5-degree Fahrenheit, 3 degrees Celsius deadband. So this keeps us from simultaneously heating and cooling throughout the day. So what is that talking about? If I'm in a building and in the wintertime, I'm heating it, there is a very good chance that I'm also air conditioning my building, because at certain points, the amount of people and the amount of sunshine that's coming in the window, or the amount of equipment that's in that building, they're all putting off the heat. Eventually, even in the wintertime, I am likely running air conditioning to provide either some of my ventilation, or to deal with humidity in the air, or just to deal with the heat that's being put off. I'm running my air conditioner. What this is trying to tell us is, don't run the air conditioner to the point where it turns the furnace on. And don't run the furnace to the point where it turns the air conditioner, so you're sitting there heating, cooling, heating, cooling. You need a 5-degree deadband in there. It heats to a certain point, but it has 5 more degrees before that air conditioner will turn on. Likelihood is that it won't reach that, and it'll go back into heating mode. Or vice versa, you cool to a point, but you have 5 degrees before it actually is going to turn that furnace on, and likely it won't. And so that's what this section is asking us to do, is to keep from simultaneously heating and cooling the building. And then it's asking that cooling towers and closed fluid coolers have either a 2-speed motor, a pony motor, if you've heard of that, a pony motor, like a backup motor, and a variable speed drive to control the fans. Those are big, huge fans on those cooling towers. And so it's just asking that we put some thought and consideration into what can be the most efficient way to run those fans. System balancing. Construction documents require that all HVAC systems be balanced, right, in accordance with generally accepted engineered standards. It requires a written balance report be provided to the owner or the designated rep of the owner, that this applies to zones with the total conditioned area exceeding 500 meters square. So 500 meters square or larger conditioned areas, conditioned meaning am I heating or cooling it, those need to have a balancing. And so air balancing, so air systems have to be balanced in a manner to first minimize throttle losses. Then for fans with systems over 1 horsepower, the fan speed has to be adjusted to meet the design flow conditions. For hydronic systems, same, hydronic systems shall be proportionally balanced to first minimize throttle losses. Then the pump impeller shall be trimmed, or the pump speed shall be adjusted to meet the design flow conditions, and with an exception for impellers or motors, pump motors less than 10 horsepower. What is this saying? What are throttling losses? It's like that escalator or elevator. These systems, it take a lot of energy to start up and get going. That energy, it's like a car. You push on that gas pedal. You push on it really hard, you use a lot more gas to go. That's why when you're in stop and go traffic, stop and go, you use a lot more fuel. It's like these systems, they take a lot more to get going. And so it's asking you to really look at those throttling losses and to make sure that we're balancing this system to cut down on those throttle losses. All right, economizers. So we talked about this a little bit earlier when we talked about the requirements for using that outside air and what are ways that you can do that. Economizers is one of the most common ways that people use free cooling, what I call it, where we, instead of paying to run this system to cool the air, we're bringing in the air outside that's cooler than what we're trying to cool it to anyway. And so an economizer is one way of doing that. So economizer brings in the outside air, runs it across the heat exchanger, kind of like an ERV, and distributes the air in, but it also has the ability to shut the cooling portion off, that refrigerant flow, just bring in that outside air and run it across there instead of, and so there's sensors and things that are built into these economizers to do that. Once the air gets up to a certain point, or you could have humidity levels on there, there are different things that you can put on these to shut off that outside air and go back to your mechanical system. So this is an economizer. When you get into this section, it says air economizers, individual cooling fan system that has a design capacity over 1,200 liters per second or 2,500 CFM, and a total mechanical cooling capacity over 6.3 tons shall have either an air side economizer or a water side economizer that provides 100% of the outside air design. So, and then it goes into some specifics. If you use a water side economizer that's capable of providing 100% of the system's cooling load at outside air temperatures 10 degrees Celsius dry bulb, 7.2 degrees Celsius wet bulb, and below. So there are some exceptions. Again, it's only required on those systems that have over 1,200 liters per second design supply capacity and total cooling capacity over 6.3 tons. So, and then if you're in a hot and dry or a warm, humid climate, you're exempted out of these economizer requirements. A hot and dry climate, one, the air might be too dry, but the hot means we're probably not going to drop down to a level where the outside temperature is cooler than what we want anyway, so we're not going to worry about jumping through the hoops on those. Humid climates, we probably don't want all that humidity in the building anyway. And then if it also says if you have an individual ceiling mounted fan system, so not a rooftop unit, but just an individual fan system on your ceiling, and it's less than 3,200 liters per second or 6,500 CFM, that's also exempted out of the requirements for economizers. Economizers are great. They work great as long as they're hooked up correctly and they have all their fault detection and they have their controls to make sure that they're really hooked up. I see a lot of economizers on buildings. I do a lot of research to see what people are doing, and I see a lot of economizers on buildings, but a lot of times they're never hooked up. They're just there. And so they only work when they work, right? All right. Then we're talking about some variable flow. So it talks about chilled or hot water systems have to be designed for variable flow and capable of reducing pump flow rates to no more than the larger of 50% of the design flow rate or whatever the manufacturer specifies. That's for chilled or hot water systems. Now, water-cooled air conditioning or heat pump units with a circulation pump that's bigger than 5 horsepower has to have a two-way automatic isolation valve on each water-cooled air conditioning or heat pump unit, and that's interlocked with the compressor to shut off the condenser water flow when the compressor isn't operating. It's, again, just controlling those times, shut things down when they're not needed. And then when we get in here, we talk about these variable flow systems some more. So air conditioning and air distribution systems have to be designed for variable airflow. right? So they have to be capable of reducing the airflow, and you can do it in a couple different ways, either by variable speed drive or variable air volume units, a VAV system, or dampers regulating the airflow through the ducts. So I see a lot of times either a variable speed drive or VAV units to address this, but you have to choose one of those. And then it says if you have an air handling unit that has a fan capacity greater than 7.5 kW, then it has to be controlled by a variable speed drive. And then there's an exception for kitchen ventilation fans. So variable speed, so it's not just all or nothing. Variable flow, variable speed. You can see this, this a lot of times we talk about these anything greater than the 7.5 kW fan capacity. Um, Once you get into these bigger fans or these bigger motors that run those fans, then they need to be variable speed. We need to have variable flow on those systems. It's kind of a theme going on, right? Boy, we covered a lot when it comes to mechanical equipment. And that's because that's where the energy use is of the building, right? As long as I'm running an air conditioning system or a heating system or a ventilation system, it's using energy. And so it, there's a lot of requirements there on how to cut down on that use. And so how do we verify that and who verifies it? We're definitely going to look at plan review for all these items, but I'm going to talk about a plan review for the design. So we want to remember that it required us to look at the design of the system to make sure that the designer of the building and the designer of the mechanical system were coordinating, they were talking, they were working together to make sure that we're designing the most efficient building as well as the most efficient piece of equipment, taking into consideration that solar heat gain coefficients, the amount of glazing, the way the building is oriented, north, south, east, or west, making sure we're looking at the design temperatures, internal and external, and the humidity levels and all of those things, and that we're not putting too much weight on energy for certain buildings and not and certain situations and not paying attention also to um, you know comfort and safety. So trying to balance all of that, and did we zone the system so that we are not running one piece of equipment for this big huge building when it has a bunch of different types of scenarios in it where we don't need the same amount of heat or cooling or ventilation in each room. So did we do that? And so that can all be verified definitely at plan review, and then of course inspection is making sure that those things were done correctly, the way that they were supposed to. When it comes to controls, that's the most important issue, right? It's also the hardest one. Not a lot of people understand mechanical controls, and so they don't know how to look for that sequence of operation or to look for those controls that shut things down when they're not needed, So I see a lot of times, yes, they've put in a time clock, or yes, they've put in their thermostat, but has anybody opened it to see that those settings they have that 5% deadband, so they're not doing simultaneous heating and cooling. They have those settings set to where they're not running on they have the 3 different day types per week, and they have, their backup power to keep it going. Do we have those things set up? And so it does take somebody actually opening those thermostats and looking in there to see, or looking if they have a system. A lot of mechanical systems on commercial buildings are done electronically. So on the computer, what are those settings set at? Are they doing that with their building systems? And so looking at those is a little bit difficult, but it is hugely important because that's where the energy use of the building is coming from. And can we shut things down when we don't need them as much? make sure you have that system balancing to make sure. That's really pretty simple because it just tells you that it requires a written balance report provided to the owner. And then that balance report has to include, how they did their air system balancing or their hydronic system balancing, etc. So making sure that you're going back there and getting that report. A lot of people will, well, I require the balance report at final mechanical inspection or before final CO. Somebody has to turn that in. But are we really going back and making sure that that's happening? So just making sure you're looking for that. Free cooling, did they use that outside air? Did they use an economizer? What did they do to shut the system down and utilize that free cooling wherever they could? Well, if they used an economizer, great. So they have this economizer. Was it hooked up? Right? Does it have its fault detection devices on there? Is it actually work? It's not one thing to just is it there, but does it work? Right? And so making sure that they are doing that whenever they can. For those variable flow pieces of equipment, do they have their, is it a VAV system? Is it some kind of do they have their 50% of the design flow rate there? What there are different things that we need to look at. If they have those pumps with motors over, 5 horsepower, are they variable speed drives? Those kind of things. Just verifying that we're meeting these energy efficiency requirements. Energy recovery. This is a tricky one because, right, it said, well, you have to have energy recovery where possible. So that's going to be subjective a little bit, but going out and making sure that anywhere that it was possible, they had their energy recovery systems, again, hooked up and working. Um, Proper ventilation strategies. Are they doing mechanical ventilation? Are they doing natural ventilation? Do they have those flow rates? Do they have healthy air moving through there? Did they hook up those fans to the ceiling or the walls if they were supposed to in those certain spaces? And so do they have their backdraft dampers on so that when the exhaust is not exhausting, it's closing and not letting air back in the building? Making sure that we have all of this is so hugely important. Efficiencies of the equipment, right? You have that list that they put in the right efficiency. It that equipment's going to be running a lot. We want to make sure that it's the right efficiency of equipment. So there's a lot to mechanical. It's the biggest part of any energy code is mechanical. But it's because that's where your energy use is and how you design the building, how you design your lighting system, how the building's being used, where it's being built. Everything about it goes to this mechanical system. So it's really important to make sure that we have that correct. All right. We talked a bit about the energy requirements for lifts and escalators and moving walkways earlier when we were in the other chapter 4 on volume 1. But there's a little bit more here in this section in volume 3, part 8, chapter 4, when it comes to these lifts and escalators. So it first starts by saying that lifts, escalators, and moving walks have to be designed and installed for the efficient use of energy. So that's great. We have to put the energy efficiency into the thought, into the design. And then it says for lifts specifically, for controls, it tells us that the lifts must be equipped with the necessary sensors and controls to reduce the energy usage. And for this purpose, the lift must include those things that we talked about earlier, the VVVF drive for the car and the door, the energy efficiency lamps used inside the car and for displays. They have to operate in that standby mode whenever it's off-peak periods. And then it also says that the power side of the lift controller and other operating equipment, such as the car lights, the display lights, the ventilation fans, they all have to be switched off when the lift has been inactive for more than 5 minutes. So a lot of the same stuff, maybe just a little bit more detail that we're finding in this section 8 than we did before. For escalators, it tells us that, it just reiterates the fact that the escalator has to be equipped with those sensors and controls at the top and the bottom landing to reduce the speed and operate at a lower speed when there's no passenger on the escalator for up to 3 minutes, and to shut down when no activity has been detected for at least 15 minutes. Same as we heard before. And then also, as we heard before, we saw that there were rainwater harvesting system in there. So remember, we talked really early today, that was a little bit longer ago, about those requirements about rainwater harvesting in Chapter 4. But we said, it's going to send us over here to Part 8, Chapter 7. So make sure you're paying attention. Well, here we are. So it goes into this whole rainwater management plan that we have to have. So while the energy efficiency requirements did give us a little bit, this is going to give us a little bit more detail on when it's required and how to do it and how it has to be maintained. So 7.2.1, the scope, says that the chapter specifies the general requirements for rainwater harvesting for different categories of the building according to their occupancy classification, together with the ancillary works of groundwater recharging, such as perforated pipe, pits, and inspection chambers. And 7.22, lets us know that it also covers the design, installation, and maintenance of elements for the rainwater drainage systems, and everything around it, how it connects to the building sewer, and so on. And then it does let us know that the stormwater drainage on the ground is not covered in this code. Just talking about stormwater drainage of the building that they're talking about right here when we talk about rainwater management plan. So let's jump to 7.4 and 7.5 to talk about the requirements and the plan. 7.4, it gives us those requirements, telling us that, every building proposed for construction on plots having more than 300 square meters or more, right, shall have facilities for conserving rainwater. So every building on plots having more than 300 square. So it's not the size of the building, it's the size of the plot. Has to have this rainwater harvesting system. That's what we're finding in 7.4. But remember, when we were back in Chapter 4, talking about the rainwater harvesting, because back there it said buildings of a total floor area of 4,000 meters square or more shall have its own rainwater harvesting system in accordance with this chapter here. So if the building floor area is more than 4,000 meters square, then you have to have rainwater harvesting. But if the plot is bigger than 300 square meters, then we have to have rainwater harvesting. So there could be a time when our building is less than 4,000 meters square, but our lot is bigger than 300, so we still have to have it. So it's just knowing how these two chapters work together to read it, all of the requirements. That's why I wanted to go through the whole thing, both sections, because one says one thing, one says another. If you put them together, there might be more times than we need it. Because what if I'm over here and my lot is smaller than 300, but I have a bigger building? Well, hopefully not. You want too big of a building on such a small lot. But you get the point. All right, so what about the plan? What does the plan have to include? So it says you have to pull a permit, and that the permit, you have to fill out an application for a permit that uses Appendix Q as your application for your rain harvesting plan. So, or your rain harvesting system. So you have to pull a permit, and you have to use this application out of Appendix Q. And it also says that you have to have a licensed plumber It's and who has to fill out the application? The licensed plumber, the owner, or his appointed person that's going to install, or a self-contained or workable part of such work. Oh, by a licensed plumber and the owner, or by his appointed person or agent to install all or self-contained or workable part of the work. So this is the application you have to fill out. You have to apply for a permit. When you apply for that permit, you have to submit the plan. And those plans, um, the application has to accompany building rainwater harvesting and drainage plans and adequate description of the proposed rainwater harvesting and drainage installation in a drawing, drawn to scale, not less than 1/100. And it gives details on what all needs to be on the plan, like things like you have to describe the building site. What is your harvesting system? Do you have a ground recharging system? We'll talk about that in a second. Is there storm drainage? What is the storm drainage system? Do you have catchment areas? What is the size of that of your catchment area? What kind of pipe and material? How is everything connected to the sewer? So it goes into, when you get into this section, I didn't put all the wording up here. I don't necessarily believe in doing that, but it goes into detail of what has to be on that plan when you apply for permit with that application from Appendix Q. And it also says that a site plan has to be included. So you have your plan that gives your description of and detail of your actual system, and a site plan also with specifics included on it that require you to turn that in as well. And it tells you in 754 that high-rise and public buildings also have to include design calculations and specifications for the various items of the work involved. So if I'm doing a high-rise or a public building, I also have to include my design calcs and specs. So then it gets into, you have to let us know the rainwater collected can be conserved and used in all useful purposes related to the use of water. So whatever rainwater you collect, you can use it for all different purposes. The amount of rainwater to be conserved depends upon the purpose of the use and the rainfall intensity at the locality and the available catchments where the rainwater is collected. So there's some things that go into this. Rainwater can also be used for artificial groundwater recharging, right? So that's saying that I collect the rainwater, I'm going to store it. So I have this artificial ground recharging that's saying underneath the ground, I'm storing this water, and eventually I can reuse it later. I can pull on it, I can recover it and use it later for something else. It's just a different kind of catchment system, basically. So I can do rooftop rainwater harvesting and artificial groundwater recharge. So then it sends us to 7.8 for rooftop or 7.9 for artificial ground recharge specifications. I'm not going to go into all of those specifications and all of those details. I'm just letting you know that the rainwater harvesting is definitely a part of energy efficiency provisions, and the code talks about it in a few places. So don't forget about that. All right. For existing buildings, the provisions of this chapter tell us in the general provisions that it's intended to maintain or increase the current degree of public safety as well as health and general welfare in existing buildings, while permitting alterations, additions, changes of use to go on. In addition, certain environmental measures to make the existing building stock sustainable is also a requirement that needs to be addressed to make buildings more energy efficient and environmentally responsive. So that's what it's telling us right there in their reasons, basically a reason statement of why we're looking at this in existing buildings. Looks at, there are some planning requirements that you have to look at, and don't forget to go through and when you're evaluating your building, to look through to make sure that when you do an addition, alteration, or a change of use, you take into consideration the planning requirements as well as those related to public safety and environmental sustainability. And those planning requirements look at, you know, does the building official has to be involved? Are there any codes violated for your proposed change of use or your addition or alteration? And it looks at things like there are different requirements for different occupancy classes and different types of construction that have to be taken into consideration. And so it gives you these, different sections to reference depending on what it is that you're looking at. And don't forget, for your existing buildings, you need to look at all of these different things. And for environmental requirements, it says additions to, alterations, or change of use of an existing building or structure shall not be permitted if they cause environmental degradation and unsustainable development in the locality. So we cannot degrade the environment or create unsustainable development when we're talking about our existing buildings. Additions to, alterations, or change of use of an existing building or structure shall not be permitted if they cause environmental degradation or unsustainable development in the locality. All right, so next let's talk about sustainability measures for existing buildings. So it says, when there are no proposals for additions, alterations, or change of use to make existing building stock sustainable, environmentally responsible, and energy efficient, the authority may propose necessary measures after evaluating the condition of the existing building. When it's found that the environmental degradation is taking place, or such as feared by experts, the measures to be proposed may include, but are not restricted to, the following. Before I show you those, what is that saying? It's saying, maybe I have this building and I was not going to propose any changes to it, but the authority finds that after they've looked at these buildings, that there's a condition existing where maybe it's starting, something is happening on this building or this site that is degrading the environment or is causing the building to use too much energy, or something is going on that now, even though somebody wasn't planning a change to it, they're going to order a change to be made. And so some of those changes could be that they ask for introduction of renewable energy, installation of rainwater harvesting, installation of groundwater recharge, or some other introduction of a low energy use source. So there may be times when something of this gets asked for your building or your site, even though you weren't proposing to make a change to it. And then it says any sustainability or energy efficiency measures suggested shall comply with all of the relevant requirements of the code that apply to it. So that's interesting and something to take note of for sure. All right. When we get into Volume 3, Part 9, Chapter 3, Conservation, this conservation chapter is not talking about energy conservation necessarily, but it's talking about conserving heritage and culture, which is just as important. Within it, it does go into sustainability and preserving, so we will talk about some of that. But I wanted to talk about the scope of this chapter. It's probably one of the best I've seen for a code. It doesn't just tell you what we're looking at, but why it needs to be addressed, and it gives some pretty compelling reasons. So let's look at 3.1, the scope that tells us that historical places Buildings, objects, and manifestations of culture, scientific, symbolic, spiritual, religious value are important expressions of the culture and heritage, the identity and religious beliefs of societies. Their role and importance, particularly in the light of the need for cultural identity and continuity in a rapidly changing world, need to be promoted. It says buildings, spaces, places, and landscapes charged with historical, cultural, spiritual, and religious value represent an important element of stable and humane social life and community pride. Without appropriate restoration, conservation, the architectural evolution in relation to socio-cultural concept of a country's heritage remains misinterpreted and actually can lead to virtual disappearance. National legislation and international treaties and regulations aim to strike a balance between the need for development and the need to conserve the environment for the future. The terminology that's used explains conservation, restoration, area conservation, and historic districts, as well as structures of architectural significance. So you can find those definitions in there and how those terms are used. Aims of construction tell us that conservation, rehabilitation, and adaptive use must consider sustainable use of natural and human-made resources. It also stresses that the access to the cultural and cultural dimension of development is of utmost importance, benefiting all the people who have access. And we need to promote historical and cultural continuity, encourage broad civic participation in cultural activities. It goes into details on how it wants us to do that, right? So that's so huge for that aim. The objectives of conservation section tells us, it lets us know that in order to integrate development with conservation and rehabilitation goals, the appropriate levels of government have to undertake this list, and it has this list of 9 things of tasks to show that the government recognizes when they're, that there's this ethic level, when that they recognize that there's a value. They recognize they have to preserve, promote, support, and even sometimes incentivize conservation and rehabilitation. So wanting to see that the government is really putting a focus there, that they value that conservation of the history and the culture. And then and ethics tell us that when working with historic buildings, every effort has to be taken to not destroy, falsify, or remove the historic evidence, keep the work to a minimum, have unswerving respect for the aesthetic, historical, and physical integrity of the cultural property, and everything has to be documented, including what methods were used and what materials. So there's a pretty high ethic in just conserving these historic buildings. And then the guidelines for conservation tell us that any work done needs to be reversible if possible. It can't affect the future work or hinder possibility of later access, as they allow the maximum amount of existing material to be retained, to be harmonious in color, tone, texture, form, and scale, and work must be done by someone who knows what they're doing. So these are different sections of this section on the historic buildings and the conservation of them, really going into why, how, what we're supposed to do, making sure that the government is paying attention and that they're concerned and they're putting a value towards it, and that the ethics are there to make sure that we're not destroying anything, we're really preserving and we're documenting what we're doing, and we have the right people doing it. So there's also a couple of additional chapters in there. Since a large part of Bangladesh culture heritage has so far remained undocumented. This preparing an inventory of heritage buildings worthy of conservation is the most important task with which to begin the process of conservation. So to start by creating this list of all of the properties out there that are historic, that add to the cultural heritage, so that we know what to fix up and when. It goes on to say that this inventory will become the National Register for Historic and Architectural Properties. It attempts to create a systematic, accessible, and retrievable record of the built heritage of the country. It will serve as a resource of materials for developing heritage conservation policies and regulations. The primary aim for of listing is to document the fast disappearing built heritage and then present it to scholars and general public in a user-friendly format which aids conservation by generating public awareness. Once a property or a building is included in the list, it becomes justifiable to undertake necessary conservation activities by formulating special regulations for its conservation or according it due protection under the Town Planning Acts or detailed area plans. So ideally, the footprint of all the listing buildings along with the guideline referred in section 3.8.2 would be included in the master plan documents for all the cities. It's really telling us why we want to have this list and the benefits of having this list. You know, if you have a building that's on this list, now that building could be protected, and we can come up with these policies and procedures for conserving those buildings that are on the list. The implementation strategy goes through the steps of involving the public in the process, protecting the building on site, retaining and or restoring original structures and architectural elements, maintain the same height, setback, ground coverage as other developments within the zone, and the adaptive reuse must follow logical sequence, considering public requirements of the region, tourist influx, social cultural context of the region under influence. So it's asking us to really look at an implementation strategy of how we get there. And then the incentives to the private owners. The section Incentives to private owners affected by conservation says that listed historic buildings, sites, and areas are usually under huge pressure from competing economic activities and hence are given rise to sharp land values. Thus, listed properties become easy target for demolition or replacement by more use-intensive or denser and taller structures with apparently better economic return, right? So it's not always beneficial or economical to fix up these buildings. It's sometimes cheaper to tear them down and start over. But so what kind of incentives do we provide to these? So to safeguard those threatened landowners, special financial incentives should be offered to the stakeholders to preserve the national and universal outstanding values. Considering them as affected people, transfer of development rights, TDR certificates, shall be introduced to protect these heritage. I think this is an amazing chapter. We want to talk about, energy conservation and conserving these historic buildings, but first they're saying we have to determine what those buildings are, create a list, document them, make sure that the public has got some input, make sure that the government recognizes the importance of them, make sure that the owners are protected, and that there's some incentive to actually fix them up and not just tear them down. So this is an amazing chapter and on conservation that I wanted to include as in this. So let's now talk, just summarize what we're doing. So while all these requirements, why do all these requirements exist in the code? I want to take you back to the very first code section that we talked about, very first thing, the rationale for sustainable green buildings. Remember that section early on that we talked about is one of the first few slides. And it reminded us that climate change is an established phenomenon affecting the environment globally, and it's recognized that buildings and the built environment play a vital role in the process, impacting on the natural environment and the quality of life, right? So we're rationalizing why we built this code, why all of these measures are in this code. And a lot of it is there's climate change out there. It's ever changing. It's global. It's not just local. It's recognized everywhere. And the built environment plays a huge role in that. Sustainable development, the concepts and approaches applied to the design, construction, and operation of buildings or to any built environment can enhance both economic and environmental benefits of the community in Bangladesh and around the world. Energy efficiency and sustainability is not an individual issue, rather an integrated and inseparable part of the building design and construction process. This code goes to great detail to make sure that it's not an individual issue, it's integrated and inseparable in the whole design. Remember the design from the outside, the inside, and everything in between. The benefits of sustainable design principles include resource and energy efficiency, healthy buildings and materials, ecologically and socially sensitive land use, and strengthen local economics and the communities, objectives vital for future development of Bangladesh. If we want to move forward and keep developing, we have to be sustainable. We have to be not tearing down our environment and making things that are not sustainable. We have to, in order to have a vital future, we have to do that. That's the rationale that we talked about in the very beginning of the code. That's written right in this code, the rationale for sustainable green buildings. It's amazing to me that rationale. That's why I bring it up in the beginning and I bring it up in the end, so that it tells us the reasons why everything got put in there. So as you reflect back on everything we've talked about today, it's important not only to remember what's required, but why. Because if we know why something's required and we believe in the why, then the how doesn't seem like such a big thing to accomplish. We want to accomplish it because we believe it needs to be done. And this code goes to great detail to help us understand why and to believe in it. It started on the outside of the building, and we talked about how to look at the outside of the building, that site, and to keep it sustainable and to make sure that we're not adding to the flooding problems. We're absorbing the water and we're retaining the water, and we're not have surfaces that just flow the water off, right? We have we take that water that is used for our sinks, and we use that for flushing, and we use that for irrigation. We have irrigation plans that look at how we're watering, and do we have those measures in place to conserve some water on the site. In addition to what we're doing, we have those plans, those landscape plans that utilize the local or the native plantings, and that we are not having a bunch of dust and and we're providing greenery. And so we've looked at the site, we've kept that rainwater, we've sized the system, appropriately. And so we've looked at the outside of the building. Then we looked at the building and what about that building do we need to do to not just conserve the energy use of the building, but to look at how we can help with the design of the mechanical equipment so that it doesn't work so hard also. So how do we do that? And looking at those windows, how many windows do we put in? What kind of windows can we put in? What kind of shading should we put in? Right? And looking at all of those things. Then we looked at, okay, here's our roof. What kind of roof do we put on? We've got our green roof that not just helps with the climate, but it helps with insulating that roof so that we're not doing a lot of heat loss through the roof. And so we have a green roof, and wherever we don't have a green roof, we have insulation. And so we've talked about how to treat that building envelope for those parts. Then we moved inside the building and we looked at our mechanical systems, our lighting systems, the ventilation systems inside the building. What kind of light bulbs are we putting in the building? What kind how do we turn them on? How do we turn them off when we need to? Are we utilizing daylight? Are we bringing in that daylight from the outside and shutting off the lights whenever we can and being responsible to pay attention so that the occupancy sensors, if nobody's in the space, those daylighting sensors are not coming on and off. And we looked about how to do that, how many watts per square foot we were allowed. And then we looked at mechanical equipment, pretty heavily at mechanical equipment. And how do we shut it down when we don't need it? How do we sequence the operation so that only the equipment that needs to be on is on, and then it shuts off when it's not needed? How do we take those fans those equipment that has big fans and big motors and use variable flows, variable speeds, try to cut down on throttling losses? And how do we utilize outside air whenever we can? If we can use outside air to cool the building, then let's do that. How do we do that? We can do that through economizers. We can shut things down and bring in that outside air, and then a lot of exceptions of when we don't have to do that or when we can't do that. We looked at how to ventilate the building naturally, how to ventilate it mechanically, and when we have to do those kind of things, and what's involved in that. Ventilation is huge for the building efficiency, for the health and safety of the people inside, to reduce condensation, to reduce pollutants, to move pollutants from out of the building, and keep fresh air flowing through. So there's indoor air quality issues that we're dealing with. And so we talked about a lot of those, so that's great. We also talked about elevators and escalators and how to make sure that those are efficient and to cut down on throttling losses there too. The startup and the stop of those uses a lot of energy, and how do we cut that down with our various drives that we could use and sensors to only have those things moving when they need to be moving, and efficient lights in them, and standby power and standby modes, etc. And so we talked about then we talked about water conservation and conserving that water, and how do we do that, and maybe using some solar hot water when it comes to those buildings that use a lot of hot water, those hospitals and things like that, hotels where we use a lot of hot water, we could use some solar thermal. Or maybe, again, low flow fixtures. We can use some low flow fixtures to conserve some water, and then conserving water through the use of the gray water. So there was a lot of things on the inside of the building. Then we talked about existing buildings. Existing buildings being conserving that energy in our thought, in our design for additions, alterations, changes of use, making sure that wherever possible we could conserve some energy, and we had to put some thought into that, into those designs for those existing buildings. And then our historic buildings and preserving the historic form and texture and nature of those buildings, and protecting our heritage and culture in doing all of it. So what an all-encompassing, all-inclusive code this is. I know that we talked that this was titled Energy Efficiency of Buildings, but this was all included in the energy efficiency requirements in the Bangladesh National Building Code. Uh, so not very many codes that I have gotten to experience will go into that range of as their minimum. And so it was good to see how all of that came together and it all worked together. And the rationale started us out, and the rationale ended us out. Here's what we're going to do, and here's why we're doing it. And they were, again, very compelling reasons. Once you believe in why you do something, then the how doesn't seem as impossible. And so we don't fight it as much. All right. Well, that is the presentation. Thank you very much for being here today, and I hope that you have learned something. I have learned a lot uh, from about Bangladesh and the culture and the history, and so I have enjoyed learning this code. I have enjoyed teaching this code, and I hope to hear from you. If you have any questions regarding anything, please send me an email. My email is right there, and I would be happy to answer any questions that we have if you just want to email me. So thanks again for your time. Have a great day.